Hi, my name is Mingi Zhang, an assistant professor at Virginia Tech. It is my great honor to present our work at AAAI 2026. Today, we present Renew, a novel global path planning framework for autonomous surface vehicle operating under dynamic disturbances, especially water current. Now let's begin. In maritime navigation, water currents significantly affect both the navigation risk and energy costs for path planning. During such coastal navigation, the vehicles ensure that a contingency maneuver always exists based on their turning maneuverability, while it is not straightforward when there exist external disturbances. Although prior work have addressed the path planning under external disturbances, a fundamental gap remains in jointly reasoning about dynamic currents, safety, and efficiency cost. Some approaches handle disturbances using fixed safety margins. Others optimize the energy by going with the flow, but focus on a single nominal path. Topological planners generate distinct routes, yet not explicitly considering adaptive safety guarantees under dynamic disturbances for a contingency maneuver. To address such challenges, our key contributions are first, identifying states that may enter non-navigable areas along with a risk-aware framework based on adaptive padding. Next, proposing a hierarchical planner for discovering topological distinct paths and optimizing an energy efficient path under disturbances. Last, the best effort strategy under the worst case conditions for feasibility of the contingency maneuver. We first define an unsafe state as a hard no-go zone where the vehicle must never enter. We then define soft no-go zone as a set of positions where the robot may enter hard no-go zone despite its best effort. To identify such soft no-go zone, we construct a set of navigation meshes by employing constrained Delaunay triangulations called the CDT. One of our key ideas is to construct a set of homotopy channels found over CDT. We use then depth-first search algorithm to find the topologically distinct channels. Without disturbances, the robot traces a regular turning circle as a contingency maneuver. However, in the presence of the disturbances, the turning shape becomes irregular, varying the no-go zone. To identify such varying area, especially when there is a noisy disturbances, we sample as per vector field distribution. Here is an example of two current direction comparisons. Using these samples, we compute the percentile of distances to closest edge and define a probabilistic collision bound. This distance is used as an adaptive padding offset from the original boundaries of the obstacle. The following example shows that after an adaptive padding, the corresponding homotopy becomes infeasible due to the blocked passage. On the other hand, another homotopy going above the island shows that the passage is still safe and feasible to guarantee the probabilistic bound. After evaluation of topological distinct channels, we compute the fuel efficiency within each channel. We evaluate the fuel cost of each homotopy channel and select the best one. Once we identify the best homotopy, we chose the optimal path within it. To validate our proposed method, we compare with the state-of-the-art approaches. Our proposed method successfully identifies an optimal path by leveraging favorable current directions in this 4-gyre environment. We also validate our proposed method in real-world scenarios. For example, in Hansando with the generally strong adverse current and complex topological structure, our algorithm is still able to find the path with the best fuel consumption. We also show that our method can adaptively choose the optimum path under varying environmental conditions, even if the start and goal positions are the same. Finally, we validate how our proposed method ensures no collision even after executing our contingency maneuver. Under dynamic disturbances, our proposed method consistently avoided collisions compared to the state of art that had collisions. In conclusion, we propose in this work safety guarantee framework based on the best effort turning under uncertainty, considering maneuverability as well as adaptively identifying no-go areas. Next, efficient hierarchical planner for discovering topologically distinct paths and optimizing a final path for energy efficient and kinematically feasible ones. We also demonstrated in an extensive simulation in realistic environment and real-world data. Our next step include some speed modulation that can achieve more gliding behavior of vehicle through the current. And also, we try to extend to the real-time current forecast or onboard estimation of the vector field with the hardware experiment. Thank you for watching our video.